to Bn, if n is in An and n is not equal to n, then the successor of n belongs to An, and finally G, n belongs to An. We now have to show that first of all there exists such a pair for the successor of n plus plus, and then we have to again prove that such a pair is unique. Okay, now define so what we do is this: we will define An plus plus from An by uniting with it or adjoining with An, the successor of n, which if you remember it is not there in An, it is in Bn, and An and Bn are disjoint, so this is originally not there in An. We are taking it from Bn and putting it with An, so that is our new An plus plus, and like that Bn plus plus is obtained from Bn by removing this. So that means we are getting the new sets by just shifting this element from Bn to An. That's all. Okay, now for this new set, what about the conditions? Let us see one by one. Is condition A true? Condition A is true because you see An and Bn were originally disjoint. So bringing one element from Bn and transferring it to An is not going to change anything. They are still going to be disjoint. Clearly, conditions A, B and C are true for An plus plus and Bn plus plus. Okay, what about condition B? Since union of An and Bn is the set of natural numbers, so transferring one element from Bn to An, actually the element is still there in the set of natural numbers, so it's not going to change anything. So the union of these two is also N, the set of natural numbers. So condition B is true. What is condition C? Condition C says that 0 belongs to An. Since 0 belongs to An and this is union of An with another set, so 0 also belongs to An plus plus. So these three conditions are clearly true with 0 belonging to An plus plus. Next we have to verify D, but keep in mind in place of n we now have n plus plus. Okay, next so we have to say that n plus 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 belongs to E. Okay. Next, since n plus plus belongs to Bn, this is coming directly from here, condition, original condition D. So by condition E, condition E says that if something is in N, its successor, something is in Bn, then its successor is again in Bn. Now that something here is this. So we have successor of N plus plus belonging to Bn. This is coming from D and E. Okay. Now, can this be equal to N plus plus? Since, okay, or one can prove by induction that in, let me just write it like this. It is easy to prove by induction that n is not equal to the successor of n for every natural number. Very easy, you just use the piano axioms and you will be able to prove this. Now we are using this fact in particular for n plus plus in place of n. So in particular, n plus plus is not equal to its successor. Okay. Now look at this. What do we have now? This element, this big looking element is in Bn, and this element is not equal to n plus plus. So that means this element will be in Bn plus plus. Thus belongs to Bn plus plus, which is just condition D if we had n plus plus in place of n. You see? So that means, and so condition D is true. Okay, now we come to E. So for E, you take an element in Bn plus plus. Next, let say, or let A belong to Bn plus plus. Then A belongs to Bn and A is not equal to n plus plus. Okay. By original condition E. Original condition E means this one. Now A is in Bn, so A plus plus will be in Bn. A plus plus belongs to Bn, and by it was axiom 4, yes. By the fourth piano axiom, A plus plus is not equal to Okay, wait, hold on. How can I make sure that a plus plus is not equal to n plus? Oh, okay, yes, a is not equal to n, so that means, am I getting it correctly? Wait, let me just see. Okay, conditions a, b and c are true. Okay, a cannot be equal to n. This cannot be equal to n plus plus. Now what is the justification for this? Since a is not equal to n, we don't write by axiom 2.4 here, and a plus plus is not equal to n plus plus. Okay, we will mention axiom 2.4 here. By axiom 2.4, a plus plus is not equal to n plus plus. This is because a is not equal to n, we have already written, but why is a not equal to n? You see, by not this one, g, yeah, by condition g, n belongs to a n. Okay, this is because by original condition g, n belongs to a n, and by, I need space for this, by original condition a, an and bn are disjoint. So what have we written here? Let us just see whether what we have written is correct or not. B have an element a in bn plus plus. That means a belongs to bn and a is not equal to n plus plus. That is fine. By original condition E, since a belongs to bn, its successor will belong to bn. But we are also saying at the same time that a plus plus is not equal to n plus plus. Why? By original condition G, n belongs to an, and since our a is coming from bn, n is in an, and these two are disjoint, so a is not equal to n, and that's why by the fourth piano axiom, which says that different natural numbers have different successors, so a plus plus is not equal to n plus plus. Now it's okay. So what is the conclusion, ultimate conclusion? A plus plus is in bn and a plus plus is not equal to this. Thus, a plus plus belongs to bn plus plus. So we have taken any element in bn plus plus and its successor is again in bn plus plus. Thus, condition E is true for Bn plus plus. Now we look at condition F. Next, let what shall we take? D, can take anything. Let us take P. Let P be any element in An plus plus such that P is not equal to N plus plus. We have to prove that the successor of P is again in An plus plus. Then what is the meaning of P being in An plus plus? An plus plus is the union of An and this element consisting of this singleton set. But P is not equal to that element, so P has to belong to An. Then P belongs to An. Okay. If P is not equal to N, then by original condition F, we have P plus plus belongs to An, because if P belongs to An and P is not equal to N, then the original condition F, that An and Bn satisfy, from there we get P plus plus belongs to An, and as such, since it belongs to An, so it will also belong to An plus plus from its definition. If okay, so if P is not equal to N, so what is the other case? P is equal to N. If P is equal to N, then P plus plus is nothing but N plus plus. That also belongs to An plus plus by definition of An plus plus. So in any case, if P belongs to An plus plus and P is not equal to N plus plus, then P plus plus belongs to An plus plus. So condition F is true for An plus plus. So only one more condition is there to check, and that is G. Finally, okay, in the gth condition, I mean G condition G, what we had, N belongs to An. So here we have to prove N plus plus belongs to An plus plus, which is true. You can see from the definition of An plus plus itself. Finally, from the very definition of An plus plus, we have N plus plus belongs to An plus plus. Thus, condition G is true for an plus plus. So these newly defined sets an plus plus and bn plus plus also satisfy all the conditions. Now also we are not, you see, we are not yet done. We have to now also prove that this pair of sets an plus plus and bn plus plus is unique, just like how we proved that a naught and b naught were a unique pair. Okay, but before we go to that, some more ink is needed. Okay. Now we prove that the pair an plus plus comma bn plus plus is unique. Let E comma F be a pair of subsets of n satisfying conditions A through G with 0 belonging to E and n plus plus belonging to F. Okay. We will now, our aim is to prove that E is equal to an plus plus and F is equal to bn plus plus. We now define two more sets. E prime. E prime is defined to be from E we are going to, okay, have I written it correctly here or here? F belongs to what was J? Oh, sorry. I think I have written it wrongly here. 0 belongs to E and okay. You see how confusing these things are. This is not n plus plus, it is the successor of n plus plus that belongs to F. Okay. Now, so what we do in E prime, from E we are going to remove n plus plus. Okay. From E we are going to remove n plus plus and we define F prime. To F we are going to adjoin that n plus plus. So what we are doing here is just the opposite of what we did while we defined an plus plus and bn plus plus. There we transferred n plus plus from bn to an. Here we are transferring n plus plus back from E to F. Okay, the role of E and F are just like the roles of An and Bn respectively. Okay, it's easy to show that the pair, this we will not do, it's quite easy to show that the pair E prime, let's not write, and E prime comma F prime satisfies conditions A through G with 0 belonging to E prime and n plus plus belonging to F prime. So these are the conditions, exact conditions are also satisfied by the pair An comma Bn. And keep in mind that according to our induction hypothesis, An comma Bn is a unique pair of subsets of n that satisfies this such conditions. So because of that uniqueness, E prime will be equal to An and F prime will be equal to Bn. I hope you understand that the conditions A through G, although we are using the conditions in several different levels of the induction, that is for sets which are at the next level An plus plus, but also for sets which are at the previous level An. But to keep track of the level, this condition is needed. This is telling you that we are at the level n. This condition is telling you that we are at the level n plus plus. Okay, if you go through the original conditions when they were first laid out, or in the hint, the way they are given, there you will get an idea of how to label the conditions for what level of pairs of sets we are saying the condition. Okay, so these sets E prime and F prime are at the same level as the sets An and Bn. So their uniqueness proves that E prime is equal to An and F prime is equal to Bn. But by the induction hypothesis, An comma Bn is a unique pair that satisfies conditions A through G A through G with 0 belonging to An and n plus plus belonging to Bn. Hence, E prime is equal to An and F prime is equal to Bn. Using these two equations, we will be able to prove that E is equal to An plus plus and F is equal to Bn plus plus. Let's see how. Now, what is E? E can be written in terms of E prime and n plus plus. How? Since we have obtained E prime by removing n plus plus from E, so E will be equal to E prime union n plus plus, and E prime is equal to an and if you go back to the definition of an plus plus, you can see that this is nothing but an plus plus. And just like that, f has been to f, if we adjoin n plus plus, we get f prime. So that means f will be equal to f prime minus n plus plus, and f prime is equal to bn and this by definition is bn plus plus, and this proves the uniqueness of the pair an plus plus and bn plus plus that we have defined. Hence bn plus plus. This shows that Pn plus plus is true, and so the induction is complete. The big induction is now complete. Now, having this pair of sets for every natural number, we will be in a position to again define those functions an and proceed exactly similarly like what we did in that first paragraph. So let's just mention some things about that. So I have written it here like this. One can now proceed to prove this. For every natural number n, there exists a unique function an from an into n. Do you recall the suggestion that was given after the hint in the exercise? We were asked to replace the domain of an that was originally given by these sets an, which has nothing related to ordering of natural numbers, because order, addition, multiplication, those things are not available to us. A unique function such that an of 0 is equal to c and an n plus plus is equal to f of n comma an of n for all n belonging to n, no, not for all n belonging to n, for all n belonging to an minus n. Yes, and the proof is exactly similar to the one we had in the first paragraph. That also I think I have mentioned here. Yes, this can be done by induction on n in a manner similar to the first paragraph of the solution. But also keep in mind that although it is similar, but some things are to be justified in a slightly different manner. Let me just give you one example.